We've been working for the past few years on an interactive analysis and visualization environment for analysts and for developers. So it's a bit of an IDE. So what I'm going to talk about today is I'm going to give you one slide on big data. I'm not going to bury you in that. You'll probably hear it all over the conference. But I am going to spend another slide on who the user is, because a lot of this talk is really about the design considerations that you have when you're building a user interface where you're trying to support large data sets. And so I'll talk about what we're trying to accomplish in this space. I'll talk about some of the challenges, and then I'm going to spend like 90% of the talk on some of the things we discovered and how you can do it if you want to actually build products that deliver big data, some of the considerations. Okay, so let's just get started. So this is a real, in a nutshell, big data data sets are basically too large to be handled any other way. And so they require new tools and new technologies to actually be able to manage them. There's a lot of talk about the 3 V's, so they are volume, velocity, and variety. And to give you an example here, 33% of companies today, like these are based on Gartner statistics and Forrester and IDC and those sorts of things. So 33% of companies are now working with data sets of 500 terabytes or better. We have velocities. By next year, they're sort of predicting that 63% of analytics will be done in real time, which is pretty amazing. And the variety is what's really significant. We're moving away from structured data sets to unstructured data sets. 80% of companies have unstructured data, and of course, we want to be able to get at that data and actually take it and actually structure it so that we can work with it and analyze it, that sort of thing. In terms of who's doing it, right now, what we have are data scientists. These are in any kind of discipline that you really want to think about. But really what they have are critical thinking skills, their model-based programming skills, and stats guys. And there's going to be a huge shortage of them. And they're predicting 150 to 190,000 vacancies in this job market in the United States alone. So if you're looking for a new career path, looks like it's good. The languages right now are kind of surprising though. Most of the languages are 90%. This is based on a KD Nuggets poll, so it's a pretty small poll, but 90% of the languages that people are using in this space are things like R, and there's a new SAS language and SQL and that sort of thing. And the languages that you would normally expect to be seeing in that space, like Java and things like that, very small percentage, right? The adoption, everybody's sort of, the Hadoop craze is going on, but it's really only representing about 9% of the market right now in terms of people who are in the space. And those are just a brief sort of summary of the applications, because they really, it's soup to nuts across the board. Sentiment analysis, fraud detection, and those sorts of things. And everybody's seen the Amazon shopping carts and their suggestions to you as to what you might want to buy, and that's all got to do with processing large data sets. Okay, so what are we trying to do in this space? Okay, so first of all, the big question is, do you actually believe that you can actually look at and understand and interpret big data? In other words, most people, what they want to do is reduce this down so that it's small data, and then they can work on the small data. Okay, and we do that too, but the point is that you have to believe that there is actually value in looking at big data, and hopefully by the end of this talk, you'll sort of see it. And then the other thing we're trying to do with what we're working on in terms of our project is we're trying to allow people to work with big data as if it were small data, in terms of things like the interactivity, the response time, the ease of use. We're trying to make it as easy to use big data as it is to use small data. And so what we've done is we've built this thing called the IV Workbench, which is really this analysis and visualization environment. And just to give you a little bit of sort of an understanding of what it is, it's a vector functional column store. It has an SQL-like language, but the actual underpinnings under the language is actually functional. It just looks like SQL, but it's actually doing column searches and this sort of thing under the hood. Okay, it's distributed. It's growable to zillions of cores, and all over the place. So, what I'm going to do is sort of talk about the things that are in orange here. We have ETL wizards and those sorts of things that we've been playing around with, but I'm really going to focus on visual inspection, just line-by-line editing and spreadsheet editing, just to keep it kind of focused in an area. Excuse me. So there's a bunch of challenges. Oop, I just want to make sure. Sorry. So there's a bunch of challenges that you really have to consider when you're working with big data that's different than small data. And that's, you've got really a bunch of potential user interface problems. And those are over on the far side of the screen there. Things like short attention span. So if you're waiting 25 seconds every time you're trying to visualize something, you're very quickly going to become very annoyed. And so you want to have, good processing speeds so that you can get the visualizations up so that you can look at your data. Things like loss of context. If you're waiting too long, you actually can forget what you were actually waiting for and actually what you were looking for. Other things like limited short-term memory. We don't want to bury people with, you want to be able to keep the interface in your face so you can actually still remember what you're trying to do. There's increased cognitive load because you're now dealing with more complex data, so you have to make your controls smarter. And I'll show you some examples of this. And you've got increased perceptual load because you're trying to look at lots of data, right? So you've got to use different techniques and pattern matching techniques to make sense of it. Okay, so that's all nice and abstract. What I'm going to do is go through a case study. And this is a case study from the VAST challenges, and you can look them up online. They have lots of these different challenges. This one is analyzing cell phone records, and we're basically looking for a social network of criminals. And so what we're going to do in this case study is we're going to look at a table of records which has a source column, a dest column, a duration, a timestamp, and a tower in it. Okay, so this is, I'm just sort of giving you the lay of the land of what we're going to look at. The phones in this are numbered 0 to 400, so they're contrived. So the sources and destinations are all these matches of 0 and 400. And the record set for the VAST study is only 9,000 records. So I made it 35 million to make it kind of interesting. And so what we're really looking for is suspicious behaviors, and I just want to let you know what that behavior is because you're now going to be analysts here. So typically you're looking for destinations that receive a lot of incoming calls. That's what drug dealers do. They receive lots and lots of calls from lots and lots of different people. So you're going to look for that kind of pattern. You're going to look for destinations that suddenly disappear and then suddenly reappear somewhere else, but they're all talking to the same people. Okay. And the third thing you're going to be looking for is, in this fake study, is cell phone 200 is a known suspect. Okay, so I've sort of given you the lay of the land here. We're going to use our tool, but you could probably try to do the same kinds of thing in RStudio or Pentaho or probably Palantir. Okay, and we're just using an internal server. It's nothing special, and it has 4 cores. Okay. So I'm going to start off just by explaining, because things are going to go by quickly at the start here, and I'm going to give you a little sort of understanding of what's going on here. So we have a little bit of code here. We're going to execute it line by line. It's an interpretive environment. So each line executes, and you see the results, and you'll see the results down here. So we're going to load the data set, and then we're going to do a summary analysis of it. That's that little second line of code there. And then you're going to see, we'll get into the visualization aspect. So it's a load, a little summarization, and then a quick query. And then we'll get into visualizing. So here we go. We're loading up. Okay, so it's loaded. Now we're going to summarize that, and that's really just doing a reduction on it. So the reduction is done, and that tells us things like how many records there are and all that sort of thing. And now we've done the quick query. So we're going through all of this stuff in real time, and now I'm opening up our visualizer. And what I'm going to do first is I'm going to look at the shape of the data. So the first thing I'm going to do is look at source records, and I'm just going to stop here and sort of explain what's going on. What we've done is we've just visualized 35 million records, and we've binned it into 20 bins. So what we're going to do now is we're going to move forward, and we're going to do fine-grained binning, and then I'll just sort of narrate what's going on as we go along, because I know you're not analysts, but I do want to give you a flavor for the speed and the ease of use. So here we are, we're increasing the granularity, and what I'm really looking for is there a pattern in this data that I can recognize? And right now, no, I can't. So I'm going to look at another column. I'm going to look at the destinations now. So that's interesting, right? Like we see down in the 0 range, there's something funny going on, and up around 300. So I'd write those numbers down for later reference. And here we are looking at days, like dates. And so what we can see here is there's about 10 days there, and then we can see some interesting little things going on in here where there's sudden spikes in the middle of the night. So again, I would make a note of that, and I'd be doing some more analysis specifically around that. And the same thing, I'd be looking for different durations, and what we're going to see here is that it's a standard distribution, so we don't care. So now I'm going to move over and I'm going to get to the chase of it, which is I'm going to look at date and destination. And again, I'm going to stop it once it's finished its 35 million search. Okay, so the interesting thing here is that now we just bin these records by date across the bottom and destination up the side. And what I can see here is that there's a lot of activity up until this point, and then there's some funny little activity up there, right? All of a sudden it picks up at the top. So basically I should explain that I actually looked at every dimension of this data. I'm only showing you like the good bit, okay? So I was spinning this, looking at all the different combinations of all these columns and adjusting different things. You'll sort of see this as we go along. So what I'm going to do is I found this interesting, so now I'm going to increase the resolution again. So now we're going to go down a little deeper. So here's our 35 million, and we can definitely see a pattern now in this data. That's kind of interesting. We see it suddenly drop off, we see it pick up. So now I'm going to go down a little further, and I'm going to take a look at the individual items. And here I notice a few items, and so again, I'm sort of cheating. What I've done here is I just took out a bunch of time, and I found a few guys I was interested in looking at up there. So what I'm doing now is a real-time query looking at a few interesting destinations. And what I do is, as I'm looking at this, I'm noticing I'm getting some cruft in the data. So you're going to see that I'm up in the top line there. I'm going to start removing values until I get down to the interesting values. Like in real time, this took me probably about 20 minutes to figure out as the terms of the puzzle. So now what I'm going to do is I'm going to actually visualize this as a social network. So I flip over, I look at it as a directed graph. My destination is the parent and my child are all the sources. And I see the directed graph. And interestingly enough, what we really notice here is that 306 and 5 and 1 and 309 are talking to the same identical people. And so what that tells me is probably these are the same guys, and they've dropped their cell phone and picked up another one, okay, which is a classic drug dealer behavior, right? So oops, I want to slow that down there just a sec. So I'm just going to back that up a bit. So that was one way of looking at the data. What I now want to do is I want to do a PageRank analysis. So these lines of code here will do a page rank analysis and tell me who the most important guys are in this data set. So what we're going to see, I'll just back it up a little further. Here we go. Oh, there we go. I want you to sort of get a sense of the timing on this. So I'm going to highlight that, and I'm going to execute this in real time. And it's found my interesting example, and you'll notice 200 appeared there, which is very interesting. He suddenly appeared. So I'm going to look at that social network again in the context of these interesting people who are considered the most important cell phone users in this set. And then what I'm going to see is that we basically have 200 at the center of these people who are talking, and they're all kind of interrelated. So in the space of about 15 or 20 minutes, I've kind of got an answer to this vast puzzle. So what do we do here? Okay. Well, really what we're doing is we're real-time tumbling of data, and what we're trying to do is explore relationships. So what that means is that we were able to, very quickly load a bunch of records, visualize it, analyze it, flip and filter it, look at it from a number of different ways, bin it. And the interesting thing is that I think you can see that we were doing that where there was really no human factors impediments. In other words, our attention span really wasn't lost. The processing's fast enough that I can manipulate and manage this data. And all of these things are sort of working together. So what that means is, so like what we learned out of this can be binned into 3 categories. There's a couple of analysis things that I noticed while I was doing this, while we've been working on this project. We have a bunch of visualization things and a bunch of interaction things. And I'm going to go through each one of these things in a bit more detail and sort of rewind what we were doing in that demonstration and take a look at it sort of in a different way. So the first thing you want to do, and if you're going to be building out these big data applications, is my belief is that you're going to want to have an integrated analysis and visualization environment. A lot of the products today that are on the market do one or the other. So they either visualize or they analyze. And where the real power is in being able to take those 2 things and put them together. So Ben Schneiderman has this thing about data visualization. He's got this mantra of overview first, zoom next, and then details on demand. I think that's great, but I think you also have to add to it all of the other things you do in analysis, like extracting and loading, transforming, scripting, and for me, scripting is actually quite key, and sorting and categorization. These kinds of things all have to be put together, and then of course there's annotation and collaboration at the end of this process. The really interesting thing is that all of these things, even though I've got them in a list, really need to be able to be done in any order, at any time. So you need to be able to go back and forth. And what I mean by that is that you have to support an iterative nonlinear task flow. So if you think about what I was doing in that demonstration, if we take it out and we pull it apart, there's some things that are done on a visualization axis, and it's really all about how we organize data. And a guy named Richard Saul Wurman came up with something called the Latch Model, and it stands for location, alpha, time, category, and hierarchy. And it turns out that he came up with this theory that he said people organize information in these ways. This is the set. So if you look at what visualizations do, is they really map to that set. And then on the other axis, we have all these analysis techniques that we can apply, summarization, clustering, etc. And if you think about it, you'll want to have this matrix where you can do any one of the things on the top with any one of the things on the left. And you want to be able to do them in any order at all because you're really trying to discover an answer to a problem. Okay? So that's all wonderful because you're looking for those relationships, but the real issue is if you can't process quickly, you're toast. Okay, so that really comes down to this next point, which is you've got to leverage server-side processing for your queries, but you also have to leverage it for your visualization, and I'm going to sort of walk through a couple of things. So here's a typical case study where, well, actually this is a benchmark, or as Dave likes to call them, bench lies. What we've got is 100 terabytes of data from from New York Stock Exchange. So this is the trading quote system that comes in off the, out of the trades that are done on the New York Stock Exchange. There's 5,000 days of data. It's 1 trillion quotes. You can see the specifications here, the 16 cores, 256 gig, that sort of thing. So these are sample queries that we've done against that data set. And what happens is we're taking this 100 terabytes, and on a small day we do a query, it takes about 18 milliseconds, and we get a working set of around 35 million records. So if you think about it, that's why I showed you 35 million records in that other example, because what we do is we take our 100 terabytes, pull it down to 35 million records, and now you can work with it quite cleanly. And it's the same thing with the large day, right? We can do a larger query, 290 milliseconds, and now you're working with a data set of about 600 million records. I'll show you the numbers on that in a minute. Okay, so now you got your data and you want to render it. We tried a whole bunch of things where we were rendering on clients using JavaScript and D3 and all these other languages, and it just didn't work. So what we ended up doing was doing all our rendering on the server and shipping bitmaps to the client. And then what we do on the client is when you touch something, we send the points back to the server and do another lookup and pull that one point out and then tell you what the point is and what's in there and that sort of thing. And so this works out a lot better because we don't care about anybody's client, right? We don't have to worry about whether it's a Windows machine and what the processing power is there. We know this, we know what this is going to be. It's well known for us. Even if it's in the cloud, like even if it's an Amazon instance, we can know what that is. So we don't have to worry about the client at all. And I can give you more specs on that later. So here are a few numbers. Okay, rendering 1 million points on the client using JS or D3 or one of these things takes about 22 seconds. If you render that on a server and do a PNG, it's about 4 seconds. Right? That's on a vanilla cloud. 10 million points, you can't do it on the client. I have yet to figure out a way of getting Canvas to render that many points. It's about 28 seconds to render on the server, so it's very fast for that number of points. And here are some points if you do binning. So that binning technique I was showing you, 1 million points a second, 10 million points is about 4 seconds. It starts to get better than linear at some point, right? 100 million, 22 seconds, 500 million, 116 seconds. So that's getting pretty slow, and I'll show you later how we brought that number down as well. Okay, so now we've got this thing we can tumble, we can do it quickly, but what we want to do is we want to leverage pattern matching. So all of those techniques at the top already exist today, right? In other words, all of those analysis techniques like aggregation, summarization, these are well-known techniques. You can look them up in papers. The really interesting thing is a lot of them can come right across. So in other words, you can actually do them at scale and use the technique. So in other words, our ability to pre-attentively process that information is all we really need to worry about, and we can do these things on the fly at scale. So what I'm going to do is I'm going to sort of give you a crash course in, well, actually I'm going to ask, how many people know about pre-attentive processing? Yeah, okay. I included this because I figured no one knew, right? Okay, so what pre-attentive processing is basically, without paying attention, you recognize patterns. Okay, and so these guys, McKinley and Burton, did a lot of studying, and they figured out that when you're working with quantitative data, you notice the position of the data, you notice the length of the data, you notice all of those things in that order. Okay, and so to give you an example, something like length means that when I look at this picture here, the bar on the end is twice as big as the other bars. And you can tell that, and you don't even actually have to think about it. This is like lower brainstem activity, and you just know it. It's interesting that things like shape, you can know that shape is different, but you can't actually map it and say that circle's twice as big as that square, right? You don't really know anything about the data. You know it's different, but you don't know how different it is. Okay, so in certain cases, you can apply these things to quantitative data, and you can apply it to other properties of data. So what we did in that example was we used aggregation to use binning to show use our pre-attentive processing capability so that you can suddenly recognize these patterns. So what this means is I can change the bin granularity, I can change the aggregation, and I can apply it to different kinds of visual attributes such as size, shape, color, opacity, and I can suddenly pick out these patterns. Right? And the nice thing is I can apply this to like opacity, and so I can show you where you don't want to live in Sacramento. So here we are looking at 10 million crime records in Sacramento, and we can easily see where we don't want to live. Okay, and that's just applying bin counts to opacity. And here we are doing a scatter, and we're now applying the same logic to size. And here we are doing it again, doing a heat map in opacity. So really, the same technique can be applied against a variety of different graph types. Again, applied to bars, histograms. So here, again, it's the same binning technology being applied across the board. So this means that you can tumble your data in a variety of different ways and experiment and explore, and that's really what it's all about. So here's the thing, though, is that plotting all the data can actually hide the data. So here's a picture of 1 million points plotted from 0 to 1 using opacity. Took about 5 seconds. And here's the same picture. Okay, so this is the same data set plotted, and you can sort of vaguely see this little oval in there, right? And it's just by applying that opacity, and really what we're doing is we're removing data points when we do that. So it turns out, and I hope you can see this. Let me see back here. Yeah, you can see that circle up there, right? Okay. So that circle is about 2,000 points in 1 million. So it turns out that this pattern matching technique can work on a reasonably small data set against like 1 million points in that kind of ratio. If you have concentrated patterns, you can see that you can pick up 200 points out of 1 million, which I think is sort of the equivalent of a needle in a haystack. Right? It's pretty interesting that your eye is tuned well enough that you can pull that out of the map. Okay, so it turns out now that we can do these patterns, now we have to start to cheat a little with visual design, because all of the rules for visual design have been written for viewing graphs, not interacting with graphs. And I think there's a big difference. So the Tufte, Edward Tufte came up with this set of fantastic rules for visual design. Okay, and you can look them up, and they're well known. This is a terrible graph, and it violates quite a few of his rules. One of his rules is that you should erase ink that has no relevance to your graph. So the thing like the 3D box and the white bar around it and that little tinted background, that should all be gone. That's just junk. And the other thing is he's cheating, right? showing 35% and 39%, but he's cut off most of the bar. So it really looks much more dramatic than it really is. So Fox tends to like to do this with their graphics. So the thing, though, is that with big data, sometimes lying and not showing all the data is a good thing. And I showed you that example. And now I'm showing you this example where this is kind of cheating. Right? We're not really showing all the data there. It gets even better. If I process it, if I image process this data using RGB technology, I can actually drop even more points out, and the pattern gets even stronger. So with small data and with viewing graphs, we follow these design rules, but with big data, we kind of got to forget those rules and got to throw them away. So the other thing is that there's that whole telling the truth with your data and showing the y-axis, and I showed you that example where we clip the tops. Well, here's an example of points from 0 to 50,000, and we're showing all the data, right? We're showing the whole bar, and we're showing it from 0 to 50,000. The problem with that is that here I'm showing the same identical data set, but I'm showing it from the min and max range, right? Which is a no-no, but it's interesting because I suddenly see a little gap in the data. So the point is that that rule of always start from 0 on a y-axis for this kind of graph, it doesn't really make so much sense anymore when you're dealing with big data. Same thing here. There's another rule. It has to do with the 7 plus or minus 2 in a cognitive, in other words, we can only remember 7 things plus or minus 2. And so therefore, if we have a legend, we shouldn't put more than 7 things plus or minus 2 on the legend because we can't maintain context between that legend and the graph. This is sort of well-known theory, right? And that's the rule. Don't use more than 7 things. Well, here's a graph that's the top 80 keywords out of Moby Dick. We ran a natural language processor over Moby Dick, found the top keywords, plotted those top keywords. So you now have 80 keywords here in a legend in series data. And the interesting thing is that one thing we can tell about this is that certain things pop. And the other thing is that we can find an area where there's an actual gap in the document. In other words, there was a point where there was really nothing important mentioned in Moby Dick. So it's kind of interesting that a rule that would be normally applied in small data can be removed in big data and suddenly have some value. Okay. So, and then of course you can always filter out the noise, right? Because it's interactive, we can always knock down those backgrounds and that sort of thing so that we can enhance. So here we're looking at Jonah, and I can move that around and I can quickly, because it's interactive, I can do other things with it. Okay, another thing is maximizing the plot ratio, the UI to plot ratio. And what I mean by that is a lot of interfaces. So these two pictures are pictures of interfaces. And the black area is the UI control area. That's where all the buttons are and that sort of thing. And the one thing you kind of notice is that most of the interface on the far side, most of the control area, most of the interface is allocated to controls. Whereas over on the right-hand side here, most of the interface has been allocated to the graphic. And why that's important is when you're looking for these patterns, you want to be able to actually get as much real estate allocated to the actual plot so you can actually look at the details in there. Okay, so we need to strike a better balance between UI widgets and controls and actual plotting. And so here's another example that our first interfaces hid the controls. We had them all hiding so that we could maximize our real estate. So we had everything in little pop-ups. And the problem with that is that you end up using these controls so extensively that you want them on the screen. So we ended up making this trade-off where we have a scrolling list of controls on the right-hand side because we want to maximize that area for the viewing of the graph. And so I think that means that these small data interfaces might have to change to handle more of the big data problem. Okay, so the other thing hand in hand with that is when we talk about those controls, they have to manage data complexity. And what I mean by that is you'll see in a lot of the small data interfaces, they make heavy use of checkboxes and things like this on the far side of the screen. Well, when you start dealing with large data sets where there's large numbers of controls, imagine having 400 cell phone numbers that I have to check each time when I want to do a query. So over here, I've got this query. It's harder to learn, but it gives me a lot more flexibility and it's a lot more compact. So we really now have this range of choices between easy to use, right? It's easy to learn and it's easy to use, but it has much more complexity when you start looking at numbers of columns and ranges and that sort of thing. Imagine if you had a range of like, say, 7,000 and you were trying to use a slider on it. It'd be very difficult, right? So we have to start looking at ways of making that easier to use, but at the same time, making them also flexible to use. And we're right in the process of working on that sort of stuff. And it's the same thing with user interface as a whole. So we've built a visual query tool, and it's modeled after MS Query. But there's a range of these kinds of interfaces. And so it's arguable that the node and link style interfaces that you see in a lot of products are great for learning. But when you start having to do filtering upon filtering upon filtering, they suddenly get very complex. By the same token, interfaces like text are hard to learn because you have to remember everything, and then on top of it, you end up in syntax hell where you've got all these brackets and everything else, you get lost. So what we're now looking at is some kind of compromise in the middle where we can try to eliminate the syntax of text and also eliminate the hell of real estate over here on this side. So we're still experimenting with that. The other thing is small data interfaces tend to update automatically. Every time you do anything, they update. That turns out to be a really bad idea in big data interfaces. So imagine you want to change the color, the size, the granularity of your bins, and say, remove the background. If each one of those operations is auto-updated, and it takes you 7 seconds to re-render the image, that's 21 seconds rather than 7 seconds. And so it changes the way you actually think about all the auto magic that people automatically do in a small data interface. And it's the same thing with executions. A lot of small data interfaces will immediately execute the query as soon as it changes. So it turns out in big data interfaces, what you want to do is you want to provide examples of the output, and you want to provide estimates of how many records you're going to get back once you hit that database. So in other words, in this example, I've got approximately 192,000 matches out of 10 million. But I really don't want to do that query. I just want to sort of play around with it until I get it right, and then I want to execute the query. And it turns out that not a lot of interfaces are doing that sort of thing. Okay, so my last point is making scripting a primary task. Okay, and why I say that is that using our interface, we can render 500 million points in about 116 seconds. But if I get really smart about my query with a very little amount of what I'll call SQL-like scripting, I can drive that time down to about 27 seconds. And if you look at that line, it's really not that complicated to kind of figure out. Now it's doing, as I say, it's doing vector functional search underneath. It's actually doing a functional query under the hood. It just looks like SQL. And the other thing is that if you use scripting, and this is really about going back and forth between visualization and analysis, is you can actually end up with a right answer or a wrong answer. And if you decouple these things where you're only doing visualization and you've got it divorced from analysis, you can actually end up with the wrong answer. And what I mean by that is if you look at the example I gave you earlier, I did a visual analysis and I discovered a set of nodes. I also did, and I didn't show this to you, I also did a Markov analysis in about the same amount of time as it took to do the page rank analysis. And I concluded there was nothing interesting in the Markov analysis. And then I did the page rank analysis and I went, oh, that's interesting. So then I was able to take that page rank analysis and I was able to couple it with another visualization and actually come up with the right answer versus the wrong answer. If I just stopped with the visualization first, it would have been wrong. So it's the ability to be able to do these things in any order that's really actually quite important. So I thought I'd just really sort of close off here with this little demonstration of another part of the interface. And this is really more of an analyst interface that would allow them to use like a spreadsheet type interface. Okay. So this is all working in a browser. I'm looking at different cells. And now what I can do is I can actually interpret them without actually having to inspect them immediately. So, really in this example, we've loaded up, 3 million records or so, and we're just sort of playing around with it. Here's the kind of scripting that's involved here. So you can actually do things like on the fly declare keys in tables and do left joins and things we call as of joins or window joins, so you can actually look at streaming data the same way. And you can just sort of, again, work with it fairly interpretively and then get your answer back. The other thing that you can do, so I'm just going to show you inspection here, right? So again, you can actually inspect out of this same environment. So really, this is just working under the kind of the Excel model. Another thing you can do is you can actually create function calls. So here is a simple summary of using this kind of function inside of a spreadsheet. So you can actually start to now build up little languages that you can use over and over again. And then this is really putting in a higher order interface so that if someone wasn't really savvy technically, you could actually build a front end that would allow them to do this using regular standard controls like checkboxes and that sort of thing. And really, it just leverages JavaScript to allow you to do this, so you can all sort of put it in the front end. The other thing that you can do, and this will just take a sort of a second to get to it, is you can actually replace the engine. So if you don't like the fact that it's a spreadsheet and it behaves like a spreadsheet, you can actually write your own spreadsheet. And in this case, here's my little sample app. And what it does is it actually allows you to, like in this case, it's just multiplying the number by 2. So any number you put in there gets doubled. I mean, it's not really that big a deal. But the point is that it then gives you power to actually deliver that kind of thing. It really opens up the interface so that you can now use DSLs and that sort of thing to allow your users to have a higher level of order. And so what I really mean by this is that if you're going to put scripting in your product, you want to support certain kinds of behaviors. And those behaviors are allowing people to script on the fly, allowing them to go back and forth between visualization and analysis, and always showing them some output. So rather than in a compiled scenario where you're constantly compiling and then waiting for an answer, you really want this stuff on the fly. And then finally, you want to be able to take this stuff and encapsulate it and turn it into domain-specific languages so that you can use it over and over again and build up your own private sort of library, if you will. So really, this is sort of a summary. It's these main points. Basically, my view is that if you have to do at least these core things that I've talked about, if you want to really deliver yourself a small data experience at scale and still provide those things like interactivity, response time, ease of use, and that sort of thing. Yeah. All right.